Nice. So it is my pleasure to introduce Hien and Don from DoorDash. Hien Luu is a senior engineering manager leading the machine learning platform team. He is passionate about the intersection between big data and artificial intelligence, as well as teaching. He is the author of the Beginning Apache Spark 2 book and is currently teaching Apache Spark at UCSC Silicon Valley Extension School. Don Liu is a senior data scientist who focuses primarily on developing and deploying machine learning models that power DoorDash's logistic engine. Before joining the technology industry, she worked as a strategy consultant, and during this time, she discovered her passion for using quantitative approaches to better understand and predict consumer behavior. This presentation will detail the DoorDash machine learning platform journey during the pandemic. Please give Hien and Don a warm welcome. Thank you.
All right, welcome everyone to this session, Building DoorDash ML Platform During the Pandemic. My colleague Don and myself are the presenter. So a little bit about us. As introduced, I lead the ML Platform team at DoorDash. I joined about 15 months ago. And prior to that, I worked at LinkedIn and a little bit at Uber. And now Don will share a little bit about herself.
Thanks. Yeah, I'm a senior data scientist on the machine learning team. I've been at DoorDash for almost 4 years now. Prior to this, I studied economics at Yale and spent a few years in consulting before switching over to data science, and I've been at DoorDash ever since.
All right. In terms of the agenda, first, Don will share a quick overview about the DoorDash marketplace, and then go into a few interesting ML use cases here, as well as some story. And then I'll discuss our ML platform journey, as well as some scaling challenges. And then we'll wrap up with a few lessons learned and the future work. So now I'm going to hand it over to Don.
Great. So I'll kick off by sharing DoorDash's mission, which is to grow and empower local economies. We do that through our last mile logistics platform and a set of product offerings. So the DoorDash marketplace consists of actually many different product offerings. The first one you're probably most familiar with, which is restaurant delivery and pickup, where customers like you and me can order food for demand, whether it's breakfast, lunch, dinner, or even special occasions and catering. The second is our new and emerging products like convenience and grocery, where you can order everything from non-food items such as sunscreen or Advil to your entire week's worth of groceries. Our third product is DashPass, which is a subscription product that is similar to Amazon Prime. It gives you savings on every order you place, as well as special offers and deals. The fourth is our B2B fulfillment. So essentially this means that when you place an order on the Chipotle app, DoorDash is the one who actually fulfills that order and makes the delivery. A huge part of what makes DoorDash compelling as a logistics platform is both the caliber and the breadth of merchants we serve. So from a core logistics perspective, this is critical for achieving efficiency of scale that benefit the entire marketplace, which I'll go deeper into in the next few slides. You probably have guessed or have heard that DoorDash is a three-sided marketplace. And like most marketplaces, it has the flywheel effect. This means that the more activity there is on the marketplace, the greater the value it will bring to all parties involved. So to go into more detail, we can start with our consumers. As we have more consumers on the platform, there will be more orders that creates more earning opportunities for Dashers. And when there are more Dashers, that improves the delivery speed and efficiency of our deliveries, which directly translates into a better experience for consumers as well. The other piece is for merchants. So as consumers place more orders, this will attract more merchants to go onto the DoorDash platform. And the more merchants we serve, the more selection there will be for consumers to choose from. And they will continue to place more orders, and this will drive more activity as well. So as this flywheel speeds up, it brings benefits to all three sides of the marketplace. It drives growth for merchants and creates greater earnings for Dashers and brings convenience and selection for all of us as customers. So next, I'm going to talk about some of the machine learning use cases at DoorDash. I'm going to focus on the typical life cycle of a restaurant delivery and talk about how we use machine learning in every stage, which consists of creating an order, order checkout, dispatching the order, and finally delivering the order. The first stage is order creation. So when a customer lands on our homepage, we want to surface the most compelling options to them. And this is where our recommendations models play a big role. So we would like to provide a personalized food ordering experience for our customers by taking into account many different factors like their past order history and preferences, as well as their current intent. For example, are they trying to order breakfast, dinner, or maybe just a snack? Second, if customers don't see anything that they find compelling on the homepage and decide to use our search feature, this is where another set of search and ranking models come into play. So when a customer searches for something like sushi, we want to show the most relevant results and also rank them by most appealing based on the speed and quality of those restaurants. Finally, at the bottom, you see promotion from a particular merchant. So this is a service that we offer for our merchants, which is to help them grow their sales by providing targeted promotions for certain items at certain times of the day. And when this works well, it's a win for all sides of our marketplace because the merchant can grow their sales, the customer can get really good deals, and also this generates earning opportunities for Dashers. Well, the next stage is order checkout. So once all the food items have been added to the cart, the customer will reach the checkout page. And there are two important pieces here. The first one are the ETAs at the top. So ETAs are really important for setting consumer expectations for when their food is going to arrive. And if we quote a time that is too long, the customer might decide that they can't wait that long and they don't want to order. On the other hand, if we quote a time that is too short or too optimistic, then it's more likely that order is going to be late, which will lead to a bad customer experience and higher rates of churn. So it's very important to have accurate ETAs, which we predict based on a number of factors such as the size of that order, as well as historical store operations and the number of Dashers we have available on the roads. This is also an area where during the pandemic, we faced a lot of issues because we observed really drastic and quick changes to delivery patterns, such as there are no longer any traffic on the road, and also merchants no longer had in-store customers. So our ETAs became very inaccurate, and we had to solve for this by introducing features that enabled a much faster feedback loop into the models. The second stage is for fraud. So like most e-commerce companies, we need to combat fraud. And at the payment stage, we use a series of fraud detection models to identify fraudulent transactions, the most common of which are things like account takeovers and stolen credit cards. And if we do predict a high likelihood of fraud, then we'll trigger certain actions, such as asking the customer for a second layer of authentication. The next stage is dispatching the order. So this is where our logistics engine takes over. It will send the order to merchants so they can start preparing the food. And it will also assign the order to Dashers so they can pick up the food and deliver it to the customer. Now, the primary job of our logistics engine is to dispatch the right Dashers at the right time for the right delivery in order to maximize the marketplace efficiency. And to do this, it actually relies on several machine learning-based predictions, such as the estimated food preparation time, which will tell us when we think the food will be ready and to be picked up. And ideally, we want the Dashers to get to the restaurant at the exact time the food is ready. The second is travel times. And this has a lot of interesting nuances, for example, such as things like traffic and weather and local events that might impact the travel times of our Dashers. Another interesting challenge in this area is, unlike, for example, Amazon orders, food orders emerge on the fly, and quality plays a huge role in the delivery. So an extra 5 minutes could be the difference between a great meal versus a terrible one. And we need to strike the right balance between efficiency as well as speed and quality for the customer. The last step is delivering the order, and this is where our Dashers take over the show. So first, we need to figure out how to invest our marketing dollars and the right acquisition channels in order to bring enough Dashers onto the DoorDash platform. And then once they're onboarded, we also need to figure out how to mobilize them at the right time. For example, we often see spikes in demand due to things like holidays or even sports games and local events. And we do that by predicting demand in advance and also identifying the right incentives that will mobilize the right number of Dashers. In terms of the delivery assignment, as I mentioned earlier, this is responsible for matching the optimal Dashers to the deliveries in order to ensure that Dashers get more done in less time and also that consumers receive the orders quickly. Finally, the last step is to deliver the food to the customer's doorstep. And this became a really critical stage during the pandemic when we introduced contactless delivery. And while this was a necessary feature, customers often had a difficult time finding their orders and would often report their food as actually being never delivered. So the solution we employed was making Dashers taking a photo of the food being delivered and sending it to the consumer. And then we used a series of deep learning models to identify whether the drop-off photo had a door in it, which was a really strong indicator that the food was actually delivered. So now that we've reached the end of the delivery lifecycle, I'll hand it off to Hien to talk about the amazing infrastructure and tools his team has built to enable all of this machine learning work.
All right, thank you, Don, for sharing those ML use cases and those interesting stories. So now I'll share our ML platform journey, which started pretty much right before the pandemic. And I worked with my team for about 15 months now, but I haven't met anyone in person yet. So I'm really looking forward to the day that I can do that. So DoorDash company has grown quite a bit in the last 2 years. The platform journey started roughly about a year ago. That's when we decided to build and invest in building a centralized platform. As you know, most different teams have slightly different needs. So it is very important to establish like the buy-in from those teams on this very idea of a centralized platform. There are some of the teams that are shown on this slide. So how do we go about doing that? One of the ways that to do that is to have the representation from each of those teams, as well as an open forum for voicing the collective needs, opinions, and also we want to be open to the idea of data scientists contributing to the platform. The model that we establish includes like a machine learning council. And that council is responsible for making cross-functional team decisions to improve transparency as well as engagement. Decisions such as like what model types to standardize on and build versus buy decisions. In addition, it also acts as the glue to help or to hold these different teams together so we can collaborate very closely and learn from each other. Now, we don't claim this approach is the only right one, but the one that has worked for us so far. In terms of building the platform, this is the mentality that we operate with. And also, it governs the way we interact with the community. I keep telling my team about being proactively helpful as when we're working with our customers. So we believe this very much sentence here, we're only successful when our customer is successful. So with that, how do we interact and how do we plan and collaborate with the whole data science community? Starting with the planning, we want to be very transparent about what we're working on, as well as the prioritizations. So we usually share some kind of a wish list at the end of the quarter to plan for the next one, and have the data scientist community and their requests and so on. Also, we ask those customers to commit in terms of giving us feedback and being early adopters. So this planning process ensures that we're building the right capability that will make the most impact. And it also helps like motivating the team member as well, because they know what they worked on will be adopted and then bring value to the whole data scientist community. Another part is we encourage the contributions from our data scientists. And this is really important for building a community. So as you know, some data scientists have a good engineering mindset and they want to contribute. And this is especially applicable in the training library area, where they know best about what they need and the kind of APIs that would be helpful. At the same time, though, we want to establish a clear working model, such that like the expectation for the code quality and sufficient testing and so on. So now I'll walk through our the pillars of our platform. This is a pretty standard set of pillars that models after the ML development process. The approach that we're building these pillars starts with thinking big, right? By working backwards from the customer to understand their needs and put together a product vision document. And then building the pieces out incrementally based on the needs, but also keeping an eye out for the long-term vision. And now I will share some technical details about two pillars. Starting with feature engineering, we have historical features and real-time features. The historical ones are generated from our data warehouse and data lake. And we have a feature service that is responsible for uploading billions of features onto a feature store. And for the real-time features, we have a framework that is built on top of Apache Flink that you see here to generate this type of features and also send them up to the feature store. At the other end, we have, for model prediction, we have a centralized prediction service based on Kotlin and C++. And in terms of model types, we currently support tree-based as well as PyTorch model. Deploying model is fairly trivial, just via some runtime configurations. And then the prediction results are monitored in terms of the quality, as well as log into our data lake for data scientists to analyze and train their models. Now, as we onboarded more complex use cases on the platform, then the interesting scaling challenges emerge, which is totally expected. So in this session, I will share two challenges and how we tackle them. First, though, when we started out, we follow a principal approach in building our prediction service. We want to make sure it starts with a strong foundation that works and scale out as needed. So we start with this, a centralized prediction service, easy to manage, monitor, and operate. And with that, we were able to support roughly about 15,000 peak predictions per second, with some unique features that we added, including model prediction in C++, the ability to do prediction requests, batching, meaning batching model requests and predictions into a single request, as well as the ability to fetch features in batches as well, because some of those prediction requests need a lot of features. And then we took on a very important and highly visible use case that Don mentioned earlier about search and ranking, which has a much higher QPS and low latency requirements. It also in the path of the user production traffic as well. So our initial approach is to scale it out horizontally and up as much as possible. But up to a certain point, the cost becomes a little bit unreasonable. So we need to evolve our prediction service into a high performant and reliable system at the same time. So if you step back and look at a spectrum of how you map machine learning models to prediction service, on one end, you have this one-to-one, right, which is great for isolations of different models. But it's not so great for hardware efficiencies and costs, unless cost is not a concern for your company. On the other end of the spectrum, we have one service for all. And there's no isolation, so you're going to run into noisy neighbor issues and such. So for us, we choose a hybrid model that's in between. That's great for isolation, but also bringing down the cost. So we essentially move the big noisy neighbors into their own clusters and scale those clusters accordingly. And that's what we did for the search and ranking use case. And with just that simple sharding approach, our prediction service was able to support up to about 10x of pick predictions. Obviously, there's a few additional overheads, such as routing requests and managing clusters. But given the number is small, we are okay with that. Then the next larger and more complex use case came in, which is about the recommendations on the homepage. So let's understand this use case a little bit more. It has much higher QoS than the previous one. And every time a customer visits DoorDash homepage, the recommendation candidates fetch and rank. And oftentimes it needs to perform like thousands of predictions at one time. So scaling out is not an option anymore due to costs and various aspects. So what do? We take a step back and going back to the drawing board with these goals in mind, right? How do we improve our system so we can increase QPS, decrease latency, and so on? And this is especially important because the DoorDash business will keep growing. The traffic's just gonna keep increasing as well. So we want to spend a good amount of time and effort to tune and optimize the system. So we look under the hood of both our prediction service and feature store and examine pretty much every layer of the stack. So starting with the first principles, right? We know the prediction requests will occur over a network, so there's going to be network latency. And along with that, there's going to be costs of serialization and deserialization of the request and response payload. And another one is we've got to make sure that our traffic is evenly distributed as much as possible. So we ended up optimizing both our prediction service and the feature store. So for the prediction service, here's just some of the optimizations we did, and you can find out more details on that blog, the URL underneath there. The first one is to avoid the hotspots. So we want to make sure that that is the case. So we use a combination of Kubernetes, cloud native service discovery, and DNS, as well as client-side load balancing. And we track and monitor this very closely. And then the second one is about dealing with large payload. We know they will take time to travel across the network. So what can we do? So payload compression is another optimization. We don't know which algorithm works best. So we took time to do a benchmark. And it turns out Z standard is the one that works best for us in our use case. So we put that into our gRPC layer and enable compression with that algorithm. And then along the way, we also discovered some of the harmless looking log statements also contributed to latency. So we went and removed those. And then on the feature store, we use Redis as our feature store. Because we're storing billions of features on there, so we went and we examined the way we store them. So we end up redesigning the data structure to storing these features. So instead of having features as a flat list of key value pairs, instead we swap to using a map or a hash data type on Redis. What this means is Redis will group related keys into a single keys to reduce the number of top-level key lookups. So that's one dimension. The other one is Redis will create a hash for each of these keys. Therefore, that will reduce the amount of memory to store these keys, right? And again, when we're talking about billions of keys, then it matters. And for the second, for the compressing complex features, in our case, is a list features that contains a list of cuisines, or restaurants, and whatnot. Similarly, we leverage compression to reduce the size. And that has multiple impacts in terms of reducing time to transfer across the network, keep the size small, and all that good stuff. And as a result, we were able to improve CPU efficiencies, reduce much of the memory footprint, and costs along the way as well. So with all that optimization, our prediction service and the feature store, we're able to support up to roughly about 6 million peak predictions per second. And we were able to onboard that recommendation use case successfully. And that was a lot of hard work and effort, but it was worth the investments from that sense. So lessons learned. There's I listed 3 here. So scaling out, the first one is scaling out is a good option to start with, but it doesn't always work when the traffic volume keeps increasing along with the business needs. It might be appropriate for like a one-time event, but if the traffic keep going up, it requires a much deeper approach. Second one is about being customer obsessed. So in addition to collaborating very closely with our DS community, we also strive to understand the business problem that they're trying to solve, as well as the business impact, because it helps us a lot in terms of how do we go about prioritizing our projects. And then the last one is big vision and build incrementally. So we have built our platform in an incremental way, and this gives us the opportunity to receive feedbacks so that we can make any necessary adjustments along the way. And this has been really helpful. And for the future work, there's a lot to do here, but here's a few that we are considering. As the prediction request volume increases, we're looking to the potential caching, either the feature values or the prediction results. I'm sure there's going to be many interesting technical challenges in these 2 areas. The second one is about generalized model serving. Up until now, most of the use cases are based on structured data. But moving forward, we definitely see there are more use cases in the realms of natural language processing, as well as image processing, and using deep learning. So we need to extend our platform to support these model types moving forward. And lastly, the unified prediction client, again, as the adoption increases, we want to provide even an easier and optimized way of making prediction requests for our customers. So I went through a lot of technical details there. There's a lot of good blogs that we have published over the last 6 months, year and a half. So feel free to check out our DoorDash engineering blog to find out more details and reading more stories about things we do at DoorDash. And with that, I want to thank you for your attention. And that's it.
Thank you, Hien and Don, for the great presentation. Before getting into the Q&A, I would like to remind all the attendees to fill out the session poll. So the first question is from Todd Liu. He's asking if you could please explain how you guys select the features to estimate ETA.
Sure, I can take your question. First off, I like to say we have actually a blog post specifically on ETAs, like feature engineering, that you should definitely check out. It'll go into more details. But in short, we use a lot of historical aggregate features at the store and day part level. And most recently, we've real-time features, which have been really useful in just like getting faster feedback loops into our models.
Thank you. And Hao Shu asks, what is the biggest change and challenge during the pandemic for building the platform?
Yeah, it's about speed. There's a lot of interesting story that Don shared. So collaborating with the DS community, understanding the needs and what are some of the pain points, that's what our immediate needs. And by collaborating very closely and building those features out incrementally, those are some of the things that we observed that are very helpful during that time.
Thank you. And William Cox asks, how do you balance DS's doing local development versus the needs of distributed systems and data protection? Local is faster but harder to create tools that work across platforms. So how you balance data sciences, you doing the local development versus the needs of distributed systems and data protection.
Don, do you want to take that one? Or you want me to take that one?
I can talk about the more of the local development. So right now, we do most of our development on Databricks, and I think the infrastructure is set up in a way that it's easy to kind of like translate the offline development code into our online serving.
Yeah, I can add to that in terms of we want data scientists to have a lot of flexibility. Start with doing local development iterations, and once they get to a state that they want to take models to production, then essentially they can sort of like clean up their model training scripts and then use our services to train those models appropriately, and then the model can be transitioned onto the prediction service very smoothly as well. So that enables both local as well as when the model is ready for production.
Great, thank you. Will Hickson asks, do you encourage data scientists to take ownership over specific models or tasks, or do all the team members work collaboratively on all models?
I can take this one.
Yeah.
Yeah, so on the data science team, we definitely encourage, and DoorDash in general as a culture, a strong ownership mentality. So usually we have one person responsible for a model or an area of the business, and that usually happens on a quarterly basis since we have quarterly planning cadence. So that could change from quarter to quarter. But we found that having this like kind of ownership, having one directly responsible person has worked well.
William Haas is asking if your team is hiring. We can skip if you want. Or
you can certainly check out the jobs section of our DoorDash homepage and see the open positions there.
Victor Yap asks, what challenges do you see in generalizing platform for NLP and image models?
Yeah, so these models are heavy in a way. They're heavy, could be large. So we need to be really careful about how to supporting these types, as well as latency as well. So I would see some of those are things that we have to watch out for. Whether that is hosting those model on a separate cluster or not, that's something that we're working through at the moment.
Bushan asks, what do you use for serving to get low latency?
Yeah, one of the things that that I mentioned is our prediction service is based on Kotlin. We're using microservices, and the actual prediction part is done in C++. That's one piece that helps with the low latency. But all the other stuff that I mentioned also contributing to the overall latencies of prediction requests. So actually there's multiple pieces, not just a single piece.
Okay, thank you. That's it for questions. Or there's one more. How tightly, two more. How tightly do data scientists teams work with your infra teams? Is there a clear division of ownership?
Yeah, I can share, and Don, feel free to jump in as well. Yeah, it's pretty clear in terms of the data scientist is responsible for the model, right? Modeling the model, figure out what feature and whatnot. The infra team, our goal is to help the data scientist to move as quickly as possible from ideas to production. So it's from my perspective, it's pretty clear division.
Nice. Nezron asks, how does the scale out work with Redis to get this high throughput?
So yeah, Redis is some of the optimization I mentioned. It's about fetching features, because sometimes there's a lot of features we got to fetch for a certain type of prediction requests. So latency, fetching from feature store and in batch. So those optimization that we did in Redis helped a lot in terms of the amount of memory and the cost as well. So those are some things that we did for improving fetching features from Redis and to improve the throughput.
That's awesome. So thank you both again for your presentation and for answering so many questions. And thank you for the attendees for joining us today in the session. And I would just like to remind everyone to update their profiles and visit sponsor booths, as well as participate in draws.
All right. Thank you, everyone. Bye.
Thank you, everyone.